So now it's time to learn about the reactions for acids and bases. Make sure you know what your acids are, what your bases are before you start doing the reactions, obviously. So just to go over what acids and bases are, Arrhenius' definition was the first one, which no longer is valid because of certain reasons you must have learned in Gen Chem. But in any case, I'll go on to the Bronsted-Lowry acids and bases. So acids give protons and bases will accept the proton. So that's the valid theory now. And then, of course, the Lewis acids and bases, which are based on electron pair donation and acceptance. Okay, so the bases will give electrons and acids will actually accept the electrons. So they're a little bit different, okay, as far as recognizing the Lewis acids and bases. So in this presentation, we are going to do all the reactions, okay, how to predict the products, how to write reactions, all that kind of thing, okay. Generally, for the regular reactions, you kind of need to know the pKa of acids and bases in order to tell whether the reaction is going to take place or not. I don't want you to use the pKa tables all the time, so you do that only when you're really highly in doubt. Otherwise, I want you to use your criteria for the strength of acids and bases to figure the strength of acids and bases, okay? So don't use the pKa tables. Lewis acids and bases, they are not on the pKa table. Their acid strength or base strength is determined on how easily they can give electrons or how easily they can accept electrons. So it's slightly different kind of a thing. So we're going to talk about 3-4 things here, when an reaction takes place. So when a reaction takes place means when you have a good acid and a good base, meaning strong acid, strong base. If you have weaker acids and weaker bases, reaction is not going to take place that well. So you learned that in Gen Chem also, okay? And of course, we talked about the fact that the only reason that acid-base reactions take place in the first place is because you end up getting weaker acids and weaker bases. If something is yielding stronger acids and stronger bases on paper when you're writing the reaction, that reaction is not going to happen in the lab, okay? So if you go and try to do it practically, it's not going to happen, okay? And so that's why we kind of need to practice a little bit of whether these reactions are going to happen or not. And knowing me, of course, I will give you reactions that sometimes don't occur. So you have to be able to see whether the reactions happen or not. So let's look at some examples here. These are very simple. I'm starting with the simple stuff where you have an acid, which you know hydrochloric acid is a known acid, mineral acid, and then water. You know the products also, okay? So what I'm trying to show you in this one is I'm going to show you how to write the arrows, okay, for these reactions. So all of these reactions that you write in organic chemistry, they're going to be electron driven. So even if we're talking about Bronsted-Lowry acids and bases, you still have to show how the proton is given or how the proton is accepted, okay? So when you look at something like HCl, HCl is very traditional acid, okay? So you have H and then of course the Cl, so you know that HCl is the proton donor, okay? So if this is the acid, then of course the water must be the base, okay, because that's going to accept. Water is also amphoteric. If you remember, it can be acidic or basic. Okay, so it's one of those kind of chemicals. So, but we know that acid is definitely the HCl here. Okay, that much we know. Which means that water is going to be accepting the proton because that's the base. You also see that in the product. So this right here, H2O accepting a proton, this is now the conjugate acid right here. And this is the conjugate base, Cl minus. Okay, so conjugate bases, remember, they're generally negative or electron rich. Okay, all right, so how does this reaction work? Well, if you look at H2O, it doesn't really have an OH, okay, or hydroxide, which we are very, used to seeing. So here's what we do. We write the electron pair on the oxygen and we say, okay, now what we have to do is we have to pick up the proton. You got to talk to yourself when you do this kind of thing. So if the oxygen is picking up the proton is going to leave by leaving its electrons on the chlorine. Remember, proton is H plus, okay? So if it's H plus, it means that it doesn't have any electrons, all right? So it's leaving without its electrons. H plus is proton. So if H plus is leaving, it has to leave its electron somewhere. So it's going to leave it on the chlorine. So chlorine then becomes the chloride. Okay, and that's really what the reaction is here. So the arrows that you need to draw are going to be this one and this one. These two arrows are what you need. Now make sure that when you draw your arrows, you draw them starting from the right place and ending in the right place. Okay, don't just randomly draw an arrow between H and Cl. Have the oxygen pick up the hydrogen. Okay, not the hydrogen pick up a hydrogen, if you know what I mean. Okay, let's look at this other reaction, which is a very typical GenChem reaction, NaOH plus HCl. So here also we know that HCl is going to be the acid and sodium hydroxide, of course, is the base. So HCl being the acid, meaning that that's going to give its proton away, and then sodium hydroxide. Now we have a traditional base. Traditional bases meaning like a hydroxide. The hydroxide now is going to pick up the proton, so you can write the arrow again like this. Okay, so just like the H2O was picking up the proton in HCl, here sodium hydroxide, the hydroxide is picking up the proton. And if you look closely, you will see that I have my arrow starting from oxygen, not from hydrogen, not from anywhere else. Okay, so it's the O is picking up the H. Okay, so now what you have is, of course, the OH combined with the H, and that gives you the water. Okay, and then Na and Cl are going to be together. So this is ionic, so I mean you write it, you know, like this, so that's fine. But that is an acid-base reaction with arrows. In this set of examples, we're going to learn how to even predict the products, okay, that you will have for a reaction. So in the previous slide, I actually gave you the product. You had to write the arrows. Now in this one here, you have to write the arrows and also write the products, okay? So first of all, when you have a reaction like this, your first task is to figure out what the acid is and what the base is, okay? And so here, HCl is your mineral acid. So this is going to be the acid, and then this is automatically the base. Now, just a little bit of a point of deflection here. If you think CH3OH and that this OH over here, this is hydroxide, it is not. Okay, this is not hydroxide. This is an alcohol group. So don't think of this as a base because it has an OH. No, it's a base because HCl is a stronger acid, because it's a mineral acid. It's an inorganic acid. So it's an acid and it's stronger than CH3OH. CH3OH, if you remember from our acid strengths, it can be an acid. The OH here is a polar bond. Okay, so this hydrogen here can be given as a proton, and it can also accept, not hydrogen, the oxygen can also accept a proton. So it can go both ways, just like water. Okay, and so you have to be careful what you're dealing with. Okay, now that we know we are dealing with acid as HCl, so let's go ahead and write our arrows out. So how do we do this? We know that proton is going to be this one right here. So what is accepting the proton? It has to be something that is electron rich because the proton is leaving without its electrons. Okay, so the only electron rich species here is the oxygen with its lone pair of electrons. So oxygen here is going to take this proton, and now you can show another bond or another arrow going towards chlorine. So we don't have to write it like this every single time. So this way you can kind of get away with just writing a second arrow coming from here. Okay, so what happened? CH3OH, that's there. But now the oxygen has accepted a proton. So this is what happened. Now remember what a proton is. A proton is H plus. So not only are you getting the H, you're also getting a plus. Also, oxygen now has 3 bonds. So if it has 3 bonds, it has a formal charge of +1. So this is how you're going to write the CH3OH with the proton accepted. And then of course you have the Cl minus. If you were writing Cl minus and you did not have a charge on CH3OH2, then you should feel like something is out of balance, because if you have a minus, you should have a plus also. Okay, so there are always counter ions there. So that should give you a little bit of a red flag that I'm missing something. Okay, all right, and you can write it like this also if you want to. I don't recommend it yet. So maybe later on when we get comfortable, then you can do this. Right now, I would recommend that you write like this. Okay, so you can clearly see the bonds. Okay, so now in the next one, we have CH3COH and sodium hydroxide. Clearly, this is the base. And carboxylic acids is, of course, the acid family of organic chemistry. So this is the acid. That is always your first task. What is my acid? What is my base? Once you know what the acid is, then you figure out, okay, which is my acidic proton? Is it this one or is it this one? And again, your proton is going to be this one here. Why? Because it is connected to oxygen, which is then creates a polar bond. A CH bond is not as polar as an OH bond. So OH bond is the one that's easily going to break. Okay, so now we have to figure out how to write this. So again, oxygen here is going to be picking up this proton. This proton then will leave its electrons on the oxygen. Okay, so now we have CH3COO, and now oxygen here is going to get a minus because the proton left its electron on the oxygen. Then what do we have? We have the sodium ion, okay, and then we have the OH, which picked up the proton. So one of these hydrogens is coming from the acetic acid or the carboxylic acid, doesn't matter which one it is. So one of the things that I sometimes end up seeing with this kind of a reaction is something like this. What is this? I have no idea what this is. Okay, so I don't want you to write compounds that just don't exist. Okay, because you think that sodium hydroxide is a covalent bond. It is not. Okay, so sodium is cation and then here is the anion. So these two are actually separate. Okay, so when the OH minus will pick up the H, it will become H2O. All right. The sodium ion then is separated, it's dissociated. It's already dissociated before also. When you put it in acetic acid, it dissociates. So it's in solution. So if you write something like this, I think you should go back to Gen Chem then, okay, or maybe not, all right? But don't write something which does not exist, all right? So don't try to create compounds that don't exist. Try to think, okay, before you write. Is this logical? Okay, all right. Then let's go ahead to the next slide. And here are some more examples. So in this case, I just have some other kind of compounds here for you. Like NH2 minus, which is a pretty strong base. I'm talking about this one right here. So it's a strong base, okay, and it's reacting with water also. So, you know, base, again, the first thing is for you to recognize what is my base, what is my acid. So anything that is negative is definitely going to be a base. Okay, so NH2 minus is the base. Water then becomes the acidic. Now, one of the things that is on this slide, which was not on the previous slides when I was explaining everything, is the pKa's. Okay, and so I want you to note the pKa is that here you have water with a pK of 15.7, and here you have, this is the base, right? So which means this is the conjugate acid. So the conjugate acid now has a pKa of 38. And remember, the smaller the pKa, the stronger the acid. Okay, and so now we're going towards weaker acids, which is really what we want. Okay, and so this is why this reaction actually is going to take place. Now you can also compare, if you want to, NH2 minus with OH minus. Okay, NH2 minus is way stronger than OH minus. So whether you compare the water and the ammonia or you compare amide with the hydroxide, in both cases you're going towards weaker acid and weaker bases. Okay, now in this case you had the pKa's given to you, so it was a little bit easier for you to see this. In an exam, I don't give you pKa's so much, okay, and in your work I don't recommend that you look at pKa's all the time. Let's look at the next reaction. Now in the next reaction you have something like an alkyne. Alkynes, if you remember, are not really very good acids. I mean, they're acidic, more acidic than alkenes or alkanes, but doesn't make them more acid. If you look at the pKa of water, I mean, it's even a weaker acid than water. Okay, so it's not really considered to be an acid, but in presence of an amide, it does become an acid because amide is way stronger, okay, of a base. And so because of that, it can, react as the alkyne can react as an acid and give up a proton, okay? So that's this reaction. And then the last reaction is going to be for an alkane conjugate base, okay? So this one right here, this is coming from an organometallic, as we call it. So CH3CH2Li. Li is lithium, of course, and lithium means that if this is positive, because lithium is a metal, it means that the carbon here must be negative. So the carbon and lithium bond is going to be very ionic, okay? And if it's more ionic than covalent, that means carbon here is very negative. Now you'll also remember that alkanes are not acidic at all. Their pK is very high. Look at that. The pK is about 50. So they're not even considered as an acid, which means that their conjugate bases are very strong bases, okay? So if they're very strong bases, then they can react even with weak acids, okay, which in this case is an alkyne. So if you remember these things, then writing these reactions will not be so hard for you. The other thing is, of course, it takes a little practice and a little time. So don't think you will know everything at one point. It takes time, okay? So just keep practicing and let us go on forward. Lewis acid-base reactions are just a little bit different. Different, as I said, because there is no proton to give. So when there is no proton to give, it's really hard for us to think, oh, what's going on here? Because, you have to look at the acid and base in a very different way. Okay, so let me show you what's going on here. So in these reactions, you will see that there's no hydrogens, there is no hydroxides. Okay, all you see is negatives and all you see is positives. So negatives mean that something is giving electrons. Positive means that it's a cation or something is positive, which means that there is no electrons there. So if something does not have electrons, it means it's a Lewis acid. If something has extra electrons, then it is a Lewis base. You might think bromide. Bromide is a base. It's a base. It's a Lewis base. Why? Because it has electrons to give. Okay, so this reaction is going to be classified as a Lewis base reaction. Okay, so in this case, there is a positive and there is a negative. If you look at the next reaction over here, in the next reaction, there is no cation or anion. So what we are looking at here is a lone pair of electron, okay, on oxygen. And here we're looking at boron. Boron is in group number 3. So there are a total of 6 valence electrons in this one. 3 from boron and then 3 that are being shared from fluorine. So which means that it's missing 2 electrons to become the octet. So it means it has an incomplete valence shell. So Lewis acids generally are going to be incomplete valence shell elements. So in this case, the oxygen then will give its pair of electrons to boron, okay, over here. Now, one of the other things that happens with Lewis acids and bases is that their products look a little bit weird, okay? So the top reaction, it's fine. You can clearly see the bond forming between carbon and bromine, and you think, okay, positive, negative, they are going to combine, obviously. But in this case, it's kind of hard to see because what you do is you do form the bond between oxygen and boron. You form the bond, but it looks a little bit weird because there is no water given out, there is no proton, none of that stuff. So it kind of looks a little weird, but don't worry about weird, okay? You have to worry about being right, okay? Don't worry about being weird. So here is the bond. Now the other thing you have to note over here is that because oxygen gave its electrons away, because of that, oxygen now has a positive. Boron accepted the electron, so because of that, it is a negative. There is still that bond between oxygen and boron, and that is the reaction that happened. Okay, so this is when you have a lone pair of electrons. The third example is that of a double bond. Okay, so you can have electrons in a negative charge, you can have electrons as in a lone pair, and now this third example is you can have electrons as pi electrons in a double bond. So here the double bond, which is the alkene over here, now that is picking up a proton. So in this case, this is a traditional acid, okay, which is a proton donor. So in this traditional acid, the alkene is picking up a proton. And when it picks up a proton, you have these two carbons. Let me erase that. So you have these two carbons, okay, which can pick up a proton. So which carbon picks up a proton? Because the double bond is between two carbons. Well, it doesn't really matter. You can put it on whichever one you want. Just remember, the other one gets the positive. Why does the other one get the positive? The other gets the positive because now this carbon here has 3 bonds only. Okay, so because it's lacking electrons, it gets a positive charge because it just formed a new bond with hydrogen. So this carbon is happy. It's got the 4 the 4 bonds on it, but the other carbon is not happy yet. Okay, so this is just one of the steps in the mechanisms of this synthesis, and so don't worry about that. Focus on just writing the acid-base reaction at this point. Okay, let's move on. So let's see if these reactions are going to occur or not, and we'll try to do this quickly, okay, so that we can finish up this topic here. So here, this is, I think I just did this reaction with sodium hydroxide, so this one should be easy enough. So this is the base, this is the acid, this is where the electrons are. These are going to pick up this proton because that proton is the acidic proton. And then, of course, you're going to shift these electrons over here. Now, you can draw the arrow up there or down here. It doesn't matter. That's entirely up to you. Just make sure it looks nice, okay? And it looks clear that you know where your arrow is starting, where it's going, okay? So will this reaction occur? First of all, yes, it's going to occur because the base is strong and the acid is fairly okay. All right, so the product then is CH3COO minus, and then H2O, and then K plus. The K plus is the counter ion for the CH3COO minus, or the acetate ion. The next reaction, alkenes. Alkenes are not even considered to be an acid. Alkynes were actually a little bit stronger acid than alkenes. So this is a weak acid. Water is also not considered to be a strong acid. So this is like a weak acid, weak base kind of a thing. So this one actually will result in no reaction, okay, because both of them are really, really weak. So nobody knows what to become, whether you're an acid or a base. Nobody decide, you can't decide between the two. So in this case, let me write it nicely, you get a no reaction. Okay, so be comfortable in writing no reaction because I am going to give you some reactions like that. Okay. The next one now, here you have an alkyne. So in an alkyne, yes, you can have an acidic proton. And then here you have a hydroxide. So hydroxide, you know automatically, oh, this is my base. Okay, so if this is the base, then of course the alkyne is the acid. Alkyne by itself can never be a base also. Well, it can be a base if you think about the electrons over here, but then this has to be an acid. Okay, so let me not confuse the topic. Let me get back on the track. So this is the base, this is the acid, which means this is the proton that I'm going to pick up. Here is my electron picking this up, and electrons are given over here. So then I get CH, triple bond, C, and then minus, and then of course I have the H2O, and then I have the sodium ion as the counter ion for the alkanide ion. So now here I can actually write as CH, triple bond, C, and A. This is fine also. You can write minus and then plus. This is also fine. Anything is okay, provided you have the right kind of charges. So let me just talk a little bit about this reaction, okay? Because in the previous slide, if you want to go back and check, you will see that we had this reaction of the alkyne with amide, okay? So one of the things that I want you to think about, okay, is that when you have an alkyne like this, which one is going to be a better base to pick up a proton, sodium hydroxide or an amide? Okay, because hydroxide is a base and amide is also a base. Okay, so which base is going to be better for the alkyne? And hopefully you are thinking it's going to be the amide. Okay, because amide is a stronger base than hydroxide, as we just talked about that. Okay, so amide is the stronger base than hydroxide, so which means that if you treat an alkyne with an amide, that reaction is more favorable, okay, than the sodium hydroxide. So how do you also decide all these things? Okay, so in some cases you do have to look at the pKa's, okay, in order to decide this. So I want you to look at the pKa for the alkanide ion, and because this is the conjugate base over here, compare this pKa to the pK for the hydroxide, and then you will find out, okay, from there. Now we did the strength of acids and bases, and so you should automatically know that NH2 minus is a stronger base than hydroxide. Why? If you don't remember why, again, because this is coming from NH3. If you add a proton to this, and if you add a proton to this, this becomes water. So which one is a stronger acid? This is a stronger acid. Okay, so if this is a stronger acid, it will give you a weaker conjugate base. Okay, ammonia is not even an acid. Okay, so for ammonia, the conjugate base is going to be stronger. Okay, again, water is not, well, okay, water is a stronger acid than ammonia. So if water is a stronger acid than ammonia, then water will give you a weaker conjugate base than amide. Okay, that's how you do all these things without looking at the pKa tables. Okay, let's look at the last one now. The last one is very nice, kind of a reaction, because here I can clearly see that I have a negative charge here, so it means this must be my base. I don't have to think too much. This must be the acid. Okay, we're doing two things over here as we are going with this. Okay, remember, we are writing the reaction out, and we are also trying to predict if this reaction is going to happen or not. So like in B, we said it didn't happen. Okay, so that's something we'll have to predict for D also. In C, remember I told you to look up the pKa. Okay, so you can figure that one out. Okay, so here is my negative, which means this is going to pick up this proton because this is the acidic proton, and then this is the reaction. So CH3, CH2, O-, and then the CH3O- picked up a proton, so you have CH3OH. And if you're thinking, oh my God, I have a minus, where is my plus? You're absolutely right. Okay, where is my plus? So this, I didn't give you a plus here. So CH3O- technically should have a counter ion to go with it, which could be a sodium ion or a potassium ion. Any of those positive ions will work. So that is a spectator ion. So sometimes we actually don't draw spectator ions out, but you have to know that they are there. Okay, so no need to worry too much about it. Okay, so these are the products that we get. Now to predict whether this reaction is actually going to happen or not. So which means now we need to look at the product and see if they are weaker acids and bases than the starting materials. So it's easier, we'll just compare the bases, okay, because we know this is a base, it's negative, and this is the base, okay, the conjugate base. So looking at these two bases, which is a stronger base, I'll give you 10 seconds to think about this. Tick tock. Tick tock, tick tock, tick tock. Okay. So CH3, CH2, O- is stronger than CH3O-. I hope you answered that. Now, of course, if you know me at all, you know that we get to the bottom of everything. Why? Okay, why is it stronger? So why is CH3CH2O- stronger than CH3O-? And that is because CH3CH2O- has more electron density because of inductive effect. Okay, so if it has more electron density, it means it is a stronger base. Now, if we are forming a stronger base here, then this reaction is not favorable. Okay, so if a reaction is not favorable, does it mean it's not going to occur at all? Sometimes yes. Okay, it's not going to happen at all, like we did in B. It's not going to happen. Okay, but that was because we had really, really weak acids and bases. In this case, the starting materials, the reactants, are actually pretty good. Okay, it's just that the products are not weaker enough. Okay, so there are ways that you can control this reaction if you really wanted to, but at this point, that's not our concern. Our concern is that, is this reaction favorable as a forward reaction? And the answer is no. It's not favorable. Why? Because we are forming stronger bases in the product. Okay, so it's not going to happen. So feel confident that it could be no also, but also know your stronger acids and bases. And that brings us to the end of this little part, okay, for writing reactions out. So make sure you're able to draw the arrows in acid-base reactions. Make sure you're able to predict the products. So if you look at the worksheet that I have for you, you have a ton of reactions in there. Please practice as much as possible. And of course, the last thing is that you should be able to predict whether a reaction can occur or not, okay, in case of an acid-base reaction.